Some events slip into the world like a whispered memo, and others arrive like a parade with brass bands and blazing spotlights. An eclipse is neither of those, really. It isn't a new object appearing in the sky, and it isn't a single destination you can point to on a map and say, there, right there, is the thing. An eclipse is a relationship, a temporary agreement between light and motion. A moment when three familiar bodies, sun, earth, moon, line up so precisely that the ordinary rules of daylight get edited gently for a little while. It's shaped as much by precision and limits as by the drama we notice. You don't move the sun. You don't stop the moon. You don't pause Earth and hold it steady beneath a shadow like a coin under a glass. Instead, you let the clockwork run and you watch what happens when geometry becomes exact. When a bright disk turns into a crescent, when the ground notices and the air notices, and your own eyes feel how quickly the world can change when the light itself is briefly redirected. A solar eclipse is not darkness falling from above. It's the moon's shadow, clean-edged and moving, sliding across Earth as both bodies travel along their paths. A lunar eclipse is not the moon turning off. It's the moon drifting into Earth's shadow and then holding there long enough for our atmosphere to paint it with the colours of filtered sunset. Two kinds of eclipse, two kinds of shadow, and a single quiet theme underneath them: alignment, limits, a system that behaves differently, not because it's emotional or mysterious, but because the angles are right. And tonight, we'll follow the evidence gently, one calm detail at a time. Back in my office, the room holds a steady background hush, just enough to keep the silence from feeling too sharp. A desk lamp pulls warm light across a folder with a simple label: Eclipses. It's the sort of label that doesn't promise constant drama. It promises timing. It promises conditions. It promises the kind of event that only happens when the room is arranged just so. Outside the window is a dark pane of sky, and inside the room, everything is a small model of what an eclipse really is. A bright source, a few clean shapes, and the shadows they cast when something passes between. The lamp is my private sun tonight. The folder is the place where the moon can cover it, on paper, in diagrams, in notes that turn circles into stories. Even the blind slats on the window, half open, make their own penumbras across the wall, bands of softened light, not fully bright, not fully dark. A reminder that shadows are rarely binary. They have edges, they have gradients, they have structure. An eclipse is a place you can't visit, only pass through. A narrow corridor of shadow moving across a rotating world. A place defined by boundaries, by what is blocked and what slips through, by what you can only see when the glare is removed. There are days when the sun is everywhere, flooding every corner of the sky with the same insistence. And then, for a few minutes, the system shows you a different ledger. What the sun looks like when a perfect disk is placed over its face. What the atmosphere does when it must borrow light from the horizon. What a shadow really means when it isn't drawn by a street lamp, but by celestial mechanics. My name is Madeline Rowe, and this is the science of eclipses for sleep. We'll begin with the simplest definition, because simple definitions are like good doorways. They let you enter without rushing. An eclipse happens when one celestial body moves into the shadow of another, or when it blocks the light from reaching something behind it. That's all. No extra requirements, just line of sight geometry, but the details matter, because the universe loves to hide its most interesting moments in the details. There are two main categories we care about tonight: solar eclipses and lunar eclipses. The names can be misleading if you're half asleep already, so let's pin them down calmly. A solar eclipse happens when the moon passes between Earth and the sun. The moon blocks some or all of the sun's light, and its shadow falls on Earth. You, standing on Earth, are watching the sun being covered. A lunar eclipse happens when Earth passes between the sun and the moon. Earth blocks the sun's light from reaching the moon, and Earth's shadow falls on the moon. You, standing on Earth, are watching the moon being shadowed. In both cases, the cast of characters is the same: sun, Earth, moon. What changes is who is in the middle and where the shadow lands. Now, there's a question that arrives sooner or later in every eclipse investigation, and it sounds innocent enough. If the moon orbits Earth once a month, and if new moon means the moon is roughly between us and the sun, why don't we get a solar eclipse every new moon? And if full moon means the moon is roughly opposite the sun in our sky, with Earth in between, why don't we get a lunar eclipse every full moon? The answer is one of my favourites because it's so quiet. It's the answer of a slight tilt. The moon's orbit is not in exactly the same plane as Earth's orbit around the sun. If you picture Earth's orbit as a flat tabletop, the ecliptic plane, then the moon's orbit is like a second tabletop tipped by about 5 degrees. Not much, just enough. That small inclination means that most months, at new moon, the moon passes a little above or a little below the exact line between Earth and sun. Its shadow misses Earth. And most months, at full moon, the moon passes a little above or below Earth's shadow. No eclipse, just the ordinary, reliable brightness of a full moon. Eclipses require more than the right phase. They require the right phase plus the right place. The moon must be near the points where its tilted orbit crosses the ecliptic plane. Those crossing points are called nodes. There are 2 nodes because a tilted circle crosses a plane twice. One node where the moon moves from south of the ecliptic to north of it, and another where it moves from north to south. These nodes are like 2 invisible gates in space. Most of the time, the moon passes through them without fanfare. But when the timing is right, when new moon or full moon happens close to a node, then the geometry lines up, and we get our eclipse. So, in the language of the office tonight, the moon doesn't just need to show up. It needs to show up at the right door, at the right hour, with the right badge. The simplest way to understand eclipse seasons is to imagine 2 invisible doorways in space and a bright clock hand that swings past them twice a year. The doorways are the moon's nodes, the 2 points where the moon's tilted orbit crosses the plane of Earth's orbit. The clock hand is the line from Earth to the sun. Most of the time, that sun line points somewhere that isn't aimed directly at either doorway. The moon can be new, the moon can be full, and still the geometry misses by a small but decisive amount. But twice a year, the sun line drifts close enough to a node that the doorway is effectively open. That opening lasts for a few weeks. That is an eclipse season, a window when new moon and full moon have a real chance of landing close enough to a node for shadows to line up. And once you see eclipse seasons as windows, the 2-week pairing starts to feel inevitable. New moon and full moon are about 2 weeks apart, so in an eclipse season, you often get a solar eclipse near new moon, and then 2 weeks later, a lunar eclipse near full moon. Or the other way round, depending on how the calendar lands. Sometimes you even get 3, not because the universe gets excited, but because the window is wide enough that the moon can hit the node neighbourhood at one new moon, then again at the following new moon, catching the full moon in between. In that kind of season, you might see solar, lunar, solar. 3 entries in the case file, all from one open doorway. It's also why eclipse maps feel so precise, especially for solar eclipses. A lunar eclipse is generous. If the moon is in Earth's shadow, the whole night side of Earth has a chance to watch. But for a solar eclipse, the moon's umbra is a narrow stamp that slides across the surface. The eclipse season tells you when the alignment is possible. The path of totality tells you where the alignment becomes exact for a few minutes. And there's a quiet comfort in that division of labour. The season is the calendar, the path is the address. If you're not at the address, you still live in the same world. You still get the partial phases, the changed light, the crescent sun projected through leaves. But totality belongs to a thin, moving corridor, and it doesn't widen just because we wish it would. So when an eclipse season opens, the sky isn't promising a spectacle everywhere. It's simply offering the conditions. It's saying the geometry is available now. The rest depends on timing, distance, and where you happen to be standing. And with that, we can turn back to the shadows themselves, the shapes they take, and what each shape allows you to see. And now we can talk about shadows properly, because shadow sounds simple until you try to draw it, and then you notice that shadows have architecture. Take a bright source, our lamp, or the sun. Put an object in front of it, my hand, or the moon. On the wall behind, you'll see a dark region where the light is blocked completely, and a softer region where the light is only partially blocked. Those 2 regions have names, and they matter a great deal in eclipse science. The darkest central part is the umbra. If you are inside the umbra during a solar eclipse, the sun is completely covered. That's totality. The surrounding lighter part is the penumbra. If you are inside the penumbra, only part of the sun is covered. That's a partial eclipse. And then there is a third region, a little more subtle, which appears because the sun is not a point of light. It's a disk, a wide, extended source. When the object in front is too small, when the moon is a bit farther away and appears slightly smaller than the sun, the umbra doesn't reach the surface at all. The geometry narrows it to a point and then flips it into a different kind of shadow called the antumbra. Inside the antumbra, the moon covers the centre of the sun, but leaves a bright ring around the edge. That's an annular eclipse, the ring of fire. Umbra, penumbra, antumbra. 3 zones, 3 experiences, all drawn by one simple fact. Light travels in straight lines, and the sun has width. Now, let's slow down and let each eclipse type take its place in the folder. When you keep a case file, it helps to give each piece of evidence a clear label. A partial solar eclipse is the most common. The moon passes slightly off-center from the sun as seen from your location, and you see a bite taken from the sun's disk. You are standing in the moon's penumbra. The world looks a little dimmer, but it still looks like day. The sky may not do anything dramatic unless the eclipse is deep, but the quality of light changes. Shadows sharpen. The sun becomes a crescent source, and that crescent can appear in unexpected places, projected through small gaps in leaves or through a pinhole in a piece of paper, turning the ground into a quiet field of tiny crescents. A total solar eclipse is rarer and more precise. Here, from your location, the moon covers the entire face of the sun. You are standing in the moon's umbra, the narrow, fast-moving core of shadow. Daylight drops quickly. The temperature can dip. The horizon can brighten in a strange, circular way. Because beyond the Umbra, the wider world is still in daylight. And in that brief interval, sometimes only a minute or two, sometimes longer, you can see parts of the sun that are normally drowned in glare. In that brief interval, the eclipse isn't just dark, it becomes an instrument. When the moon covers the photosphere, the bright surface of the sun that normally overwhelms everything else, the sky gives you permission to notice layers that are always present, but usually hidden in glare. The most famous is the corona, the sun's outer atmosphere, extending outward in pale structure. It can look like fine hairline threads. It can look like long streamers. It can look like a soft, uneven halo, brighter in some directions and fainter in others. None of those shapes are arbitrary. They trace the sun's magnetic field, because the corona is made of hot, thin plasma that is guided by magnetic lines, the way iron filings are guided by a magnet, only on a vast scale. There is a calm strangeness here that's worth pausing on. The visible surface of the sun is hot enough to glow white, yet the corona above it is far hotter still. On paper, that seems backwards. Heat usually fades as you move away from a source. The reason the corona can be so hot sits in the physics of magnetic fields and motion. The sun's churning interior twists and stresses magnetic field lines. Those fields store energy, and when they rearrange, reconnect, or ripple in waves, some of that stored energy can be converted into heat. A total solar eclipse doesn't solve that problem by itself, but it gives you a direct look at the place where those magnetic structures are written into light. At the very edge of totality, another layer can briefly announce itself, the chromosphere, a thin region above the photosphere that can show as a pinkish rim along the moon's silhouette. And with a careful glance, you may notice prominences, arcs and loops of glowing plasma rising beyond the sun's limb, held in place by magnetic fields. They look delicate, like brush strokes, but they are immense structures compared to Earth, suspended above a star that never stops moving. If you like to keep a case file mindset, the eclipse offers a short, quiet checklist you can carry without effort. How far do the coronal streamers extend? Do they look more concentrated along the sun's equator, or more evenly distributed around the disk? Are there bright plumes in certain directions? These impressions connect to the sun's longer rhythms because the global shape of the corona changes with the solar cycle as magnetic activity rises and falls over years. You don't need to measure it precisely to feel the idea. The corona is not a fixed crown. It is a changing outline, updated slowly by magnetism and time. Modern science doesn't rely only on eclipses to study the corona. There are coronagraphs, telescopes that block the sun's disk artificially, and there are spacecraft that image the sun continuously and sample the solar wind directly. But eclipses still matter, because the moon is an exceptionally good occulting disk. It covers the photosphere with a sharp natural edge, and the surrounding darkness can reduce certain kinds of scattered light. For a few minutes, the geometry does the optical work for you, and faint structures that are otherwise lost become easier to capture from the ground. So when we say that, during totality, you can see parts of the sun normally drowned in glare, we're not speaking loosely. We mean that the eclipse reveals the sun's atmosphere as a structured place, shaped by magnetic fields, threaded with plasma, and connected to the solar wind that flows outward through the solar system. With that filed gently into the folder, we can return to the other eclipse types, the ones that change the light without fully switching the day off. An annular solar eclipse is a different kind of precision. The alignment is excellent, but the moon is a bit too far away in its orbit to fully cover the sun. The moon appears slightly smaller than the sun, so at maximum eclipse, a thin ring of sunlight remains visible. You are in the Umbra. The light is eerie and reduced, but it never becomes night, because the sun is never completely covered. And then there is a hybrid eclipse, which is rare enough that it feels like a footnote, but it is a real footnote in the physics. Along some parts of its path across Earth, the eclipse appears annular. Along other parts, it appears total. This happens because Earth is curved, and the distance from the Moon to the observer changes with curvature and elevation. The shadow geometry is right on the edge between Umbra reaching the ground and Umbra not quite reaching. A small change in distance decides which version you see. Solar eclipses, then, are a story about the Moon's shadow falling on Earth. The Moon is the small object near us, so its shadow is narrow, and it moves quickly. The Umbra, the region of totality, can be surprisingly small on the ground, often more like a corridor than a continent. That's why total solar eclipses are so local. You can be a few hundred kilometers away and see only a partial eclipse, while someone else stands in the thin line of totality and watches the sun disappear completely. And because totality is so local, eclipse maps become their own kind of evidence, the paper trail of a shadow that will exist only once in one narrow sweep across a rotating Earth. Those maps can look like travel documents, curved lines, bands, timestamps, but underneath they are just geometry translated into geography. The Moon's Umbra is a cone of shadow extending into space. Earth is a curved surface moving through that cone. Where the cone intersects the surface, you get a footprint. As time passes, that footprint slides because the Moon continues along its orbit and Earth continues to rotate beneath the incoming sunlight. That is why the path curves. It isn't a flourish. It's the natural consequence of projecting a moving shadow onto a spinning sphere. If you could freeze Earth and look down from far above, you'd see the shadow stamp a track. If you could freeze the Moon and let Earth turn, you'd see the track skew in the other direction. In reality, both motions happen together, and the path becomes the combined result of several steady movements, all of them predictable. The width of the path is its own quiet story. It depends on the size of the Umbra when it reaches Earth, and that depends on the Moon's apparent size in the sky. When the Moon is closer, near perigee, its shadow cone is effectively wider where it meets Earth, and the path of totality can broaden. When the Moon is farther, near apogee, the cone narrows, and totality becomes harder to achieve at all. At the margin, the Umbra can fail to reach the ground, and the alignment becomes annular instead. Maps also carry a second set of boundaries, not just where totality happens, but where the eclipse is partial. The penumbra covers a much larger region, so partial eclipses can be seen from broad areas that may span continents. This is why two people can share the same eclipse day, but not the same eclipse experience. One person sees a shallow bite in the sun. Another stands in the thin line of totality and watches the photosphere vanish. If you want one more piece of vocabulary for the file, strictly as a label, not as an assignment, you can think in terms of contacts. First contact is when the Moon's disk first touches the sun's edge. Second contact is when totality begins for an observer in the Umbra, the moment the last bright arc of the photosphere disappears. Third contact is when totality ends, when the first arc of photosphere returns. Fourth contact is when the Moon finally leaves the sun entirely. These aren't mystical moments. They're the points where one edge crosses another edge, and they're useful because they let observers compare timing and geometry. There's also a reason modern predictions have become so precise. The Moon's edge is now mapped in detail. The lunar limb is not perfectly smooth. Mountains and valleys change exactly how sunlight leaks through near totality, shaping the beads and the diamond ring moment at the start and end of totality. With accurate limb profiles and refined orbital models, predicted contact times and eclipse paths can be calculated with impressive precision, because in a narrow corridor measured in seconds and kilometers, the shape of the edge matters. So an eclipse map is not a prophecy, it is a calculated footprint, where the shadow will go, how wide it will be, and how long it will linger at any one point. And once that is filed away, the contrast becomes even clearer. Lunar eclipses feel generous not because they are more powerful, but because Earth's shadow is larger and the event belongs to the whole night side at once. Lunar eclipses, by contrast, are generous. Earth is the shadow caster, and Earth is large. Its umbra at the distance of the moon is wide enough to cover the moon easily. If you can see the moon and a lunar eclipse is happening, you can watch it. Lunar eclipses are visible over an entire night-side hemisphere of Earth. The show belongs to anyone under the right sky. So solar eclipses are narrow and fast, with a shadow that races across Earth. That narrow corridor of totality, the umbra on the ground, has another quiet lesson tucked inside it, one that people feel instinctively even if they never name it. Totality has a duration, and that duration isn't a single property of the eclipse, like a label on a folder. It's a property of where you are standing inside the shadow, and how the shadow meets the curve and rotation of Earth. If you stand near the centerline of the Umbra, the path's most central track, the moon covers the sun more deeply and more cleanly. You get the longest version of totality available at that moment. But if you stand closer to the edge of the Umbra, you're skimming the boundary, where the shadow is thinner and the sun is only just fully covered. There, totality can shrink to seconds. Same eclipse, same day, two very different experiences. Because the shadow is not a blanket, it's a moving cone intersecting a round, turning world. The speed of that intersection matters too. The moon's shadow isn't moving on its own the way a bird moves. It's the result of several motions layered together. The moon's orbit around Earth, Earth's rotation beneath it, and Earth's orbit around the sun that sets the incoming direction of sunlight. Add them up, and the shadow can sweep across the surface fast enough that it feels like it's hurrying, even though the system itself is only doing what it always does, steadily, mechanically, without urgency. And then there's the angle of approach, which is one of those small details that changes everything. Sometimes the umbra strikes Earth more directly, and the corridor on the ground is broader. Sometimes it arrives at a slant, and the corridor narrows, like a flashlight beam grazing across a wall. A steeper geometry can give you a wider path and more time in the dark. A shallower geometry can pinch the experience down, even when the alignment is still excellent. Distance quietly joins the conversation here as well. The moon's orbit is slightly elliptical, so its apparent size changes. When the moon is closer, its umbra can reach Earth more robustly and the corridor can widen. When it's farther, the umbra can shrink or fail to reach the ground at all, shifting the eclipse toward annular territory. It's the same reason the Ring of Fire exists. Not a change in the sun, not a trick of perception, but a small, measurable change in size and distance. Even your height above sea level can make a difference at the margins. A mountain ridge rises into the shadow a little sooner than a valley floor, simply because it's closer to the moon by a small amount. It won't turn a partial eclipse into a total one. But when you're near the boundary, when the shadow is already asking for precision, small distances can decide how the edge feels. and how quickly the light returns. In the office, I think of it like this. Totality isn't a single stamp pressed onto Earth. It's a moving seal, and your location determines how fully the seal meets the page. Stand in the middle, and the imprint is bold and complete. Stand near the edge, and you catch only the thinnest impression before it slips away. And that's part of what makes eclipse maps feel so honest. They aren't promising you a general experience. They're offering you an exact appointment, a particular line on Earth, at a particular time, where the geometry becomes strict enough that daylight is briefly refiled as something else. Once you've held that idea, shadow as corridor, duration as position, darkness as a moving geometry, then the lunar eclipse that follows feels like the complementary chapter, not a corridor on Earth, but a whole moon passing through Earth's shadow, slowly enough that you can watch the boundary advance like a hand on a clock. Now, let's open the lunar eclipse folder properly, because its pace is different. Solar eclipses hurry, lunar eclipses linger. A lunar eclipse begins as a full moon, bright and familiar, because the moon must be opposite the sun in our sky with Earth in between. As the event starts, the moon first slides into Earth's penumbra. This penumbral phase can be subtle. The moon may look slightly dimmer, as if someone has lowered the contrast on the scene rather than turning down the lights. If you're not watching for it, you might miss the first change entirely. Then the moon touches Earth's umbra, and the eclipse becomes easier to read. A dark bite appears on the moon's disk, but this time the bite is Earth's shadow. The edge of that shadow is curved, a simple geometric consequence of a spherical Earth casting a round shadow into space. As minutes pass, the shadow advances steadily. The moon becomes a half-lit world, then a thin arc, and, in a total lunar eclipse, a fully shadowed disk. And here is the part people remember. During totality, the moon often does not disappear, it glows. The moon glows because Earth's atmosphere doesn't end sharply. Sunlight skims through the ring of air around Earth at sunrise and sunset along the planet's limb. That air bends some of the light inward, refraction, guiding it into the umbral region where, in a vacuum, you'd expect deeper darkness. On that long path through the atmosphere, shorter wavelength blue light is scattered more strongly, while longer wavelength red light travels more efficiently. The result is a moon lit by filtered, refracted light, as though it's illuminated by a ring of sunsets around Earth. The exact shade is not fixed. Some lunar eclipses are bright copper, others are deep brick red. Some are so dark they feel like charcoal, with only a faint outline holding the moon in place. This variability is a clue, not a mood. It reflects the state of Earth's atmosphere at the time, how clear it is, how much dust or aerosol is present, how strongly certain wavelengths are absorbed. In other words, a lunar eclipse can act like a rough, global probe of atmospheric transparency along Earth's limb. And because lunar eclipses move slowly, they give you time to notice the difference between a line and a gradient. The umbral boundary is not a razor edge. It is a region where the light level drops steeply. You can watch surface features fade and return. You can watch the moon's familiar face become unfamiliar, not because the moon changes, but because the light reaching it has taken the long way round. A solar eclipse can feel like a sudden edit to the day. A lunar eclipse feels like a slow hand turning. That is why people often describe lunar eclipses as calm, even when the idea, Earth's shadow in space, sounds dramatic. The event gives you enough time to understand what you're seeing while you're seeing it. And that brings us back to the sentence we've already filed. A lunar eclipse is a whole moon passing through Earth's shadow, slowly enough that you can watch the boundary advance like a hand on a clock. Once you've watched that slow hand complete its motion, the longer rhythms start to make sense. Eclipses are rare in one place, but they are not rare in the system. Given enough time and enough records, they repeat in families. Ancient observers noticed that eclipses repeat in patterns, not perfectly because the system is complex, but well enough that a careful record can reveal a cycle. One of the most famous eclipse cycles is the Saros. It's roughly 18 years, plus about 11 days, plus about 8 hours. After one Saros, the Sun, Earth, and Moon return to nearly the same relative geometry. The Moon is at a similar phase, near a similar node, and at a similar distance. That means an eclipse of a similar character often occurs. But the plus 8 hours matters, because Earth rotates. 8 hours later means the next eclipse in the Saros series is visible from a different longitude. The eclipse path shifts westward by roughly a third of Earth's rotation. If you wait for 3 Saros cycles, about 54 years, those extra 8-hour shifts add up to about a full day. And the geometry plus Earth's rotation brings you back closer to the same longitude. That 3 Saros span is sometimes called the exoligmos. It's not perfect, but it's closer in terms of where the eclipse is seen. There's one more layer to these repeating patterns that feels worth filing, because it explains why eclipse seasons don't stay pinned to the same calendar dates forever, and why eclipse families have beginnings and endings. The nodes, the 2 gates where the moon's orbit crosses the ecliptic, do not stay fixed in space. They drift slowly around Earth. This motion is a kind of precession. The orbit's orientation changes over time, and the crossing points slide. The result is gentle but consequential. Eclipse seasons arrive on their own schedule rather than on the same dates each year, because the Sun has to meet the moving nodes again before alignment windows open. If you picture the nodes as hinges on a slightly tilted ring, those hinges slowly rotate around the ring. The Sun's line of sight crosses them season after season, but the appointments creep. A season that arrives in one part of the calendar now will, years later, arrive a little earlier, and then earlier still, because the gates have moved. This drifting is also part of why Saros cycles create families rather than exact reruns. A Saros brings the moon back to a similar phase and a similar relationship to the nodes, but similar is not identical. Tiny differences remain. The latitude of the moon's shadow, how far above or below Earth's center the alignment passes, shifts slowly from one event to the next in a series. Over decades, the path slides. Over centuries, the character of the eclipse changes. That's why Saros series have lifetimes. A series can begin with an eclipse that barely qualifies, often a partial eclipse near one of Earth's poles, where alignment is close enough for the penumbra to graze the planet, but not close enough for a deep event. Then cycle by cycle, the geometry inches toward more central alignments. For solar eclipses, total or annular eclipses can appear and persist for many events as the path migrates across Earth's mid-latitudes, and then the slow drift continues, carrying the series away again, until it ends with another set of marginal eclipses near the opposite pole. Seen that way, an eclipse family is a long case that spans generations. It opens with faint evidence, grows into clear and dramatic events, and then fades out as the geometry moves on. The system isn't changing its rules, it's letting the same rules play out over long time scales. I like this detail because it keeps the story honest. The sky repeats, but it doesn't loop perfectly. it advances. It carries rhythm. In cycles, you can track. But it also carries drift, the quiet kind that makes every eclipse both part of a family and singular in its exact path and timing. And from that long view rhythm, it's a small step back into history, into the human habit of recording these events, comparing them, and learning what they reveal about both the moon's motion and Earth's own slightly unsteady clock. Eclipses have a second life beyond the moment itself. They become a form of writing. Not words on paper at first, just marks, a date, a place, a description of the sky behaving oddly. But over centuries, those marks accumulate into something that looks like the earliest kind of astronomy. Not a theory yet, but a ledger. A record of when the clockwork of the heavens clicks into a rare alignment. That is where the long cycles begin to matter, because cycles are what you notice when you have enough entries in the book. One of the most famous is the metonic cycle, a way the lunar phases return to nearly the same seasonal dates after about 19 years. It's not an eclipse cycle in the strict sense, but it's a calendar cycle, one of the patterns that helped people keep lunar months and solar years in conversation. And that not perfectly is where the science gets deliciously careful, because the ledger doesn't only teach us about the moon, it teaches us about Earth. When astronomers compare ancient eclipse records to modern calculations, running the celestial mechanics backward in time, they find something subtle. If you assume Earth has always rotated at exactly today's rate, the old eclipses don't land where the records say they did. Over millennia, the mismatch becomes ours. That doesn't mean the records are useless. It means Earth is not a perfectly steady timepiece. Earth's rotation changes slightly over time, nudged by tides, by shifting mass in oceans and atmosphere, by interactions between the mantle and core. The result is that time, as measured by Earth's spin, is not identical to time kept by the gravitational dance of the orbit. In eclipse work, that difference shows up as a quantity called delta T, a way of accounting for the fact that a planet is a living, dissipative body, not an ideal clock. So eclipses, simple as they are in geometry, became one of the ways humans discovered that Earth drifts a little from perfect punctuality. And the story doesn't stop in antiquity. The same careful timing and edge measurement show up in modern eclipse science in a different form. The edge of the shadow as a measurement tool. If you listen closely to eclipse talk among astronomers, you'll hear a fascination with the limb, the boundary of the moon's silhouette, with its mountains and valleys, the boundary of the sun's bright disk, the boundary of darkness on the ground. Near totality, those boundaries become exquisitely informative. The beads of sunlight that appear just before and after totality, Bailey's beads, are not only beautiful, they encode the lunar limb profile, where the moon's valleys let sunlight through and where mountains block it. With precise timing, the beads can help refine predictions and, in some research contexts, even inform measurements related to the sun's apparent shape. Modern eclipse prediction has become almost eerily good because the inputs have become so good. Detailed lunar limb profiles from lunar orbiters, refined gravitational models, improved time standards, and an ever-growing archive of observations. So when the case file says an eclipse will be total at a particular place for a particular number of seconds, that number is not a vibe. It's the outcome of a long chain of measurement. The shape of the moon's edge, the Earth's rotation, the gravitational solutions for three-body motion, the geometry of shadow cones. And I love that, because it turns the most dramatic sky event into something almost clerical, a slow accumulation of accuracy, a world where the spectacle exists, yes, but it exists because the numbers are steady enough to earn our trust. So in the Eclipse archive, you can imagine two kinds of notes on the same page. One note says, the light changed, the air cooled, the world went quiet. And the other note says, the timing was off by minutes until we corrected for Earth's rotation, and then the old record fit again. In one folder, beauty and precision sit side by side. And that brings us back to the present-day eclipse, not as a myth, not as an omen, but as a moment when the universe lets us test our understanding by watching an edge move across the world. These cycles are a wonderful example of how the sky offers repetition without rigidity. The pattern is strong enough to track, but not so rigid that it becomes boring. Each eclipse is both a member of a family and a unique event. In the office tonight, I keep these cycles like old index cards. Not because we need them to enjoy an eclipse, but because they remind us that the sky has rhythms that can be learned and trusted. Now, before we go further, there's a related phenomenon that people often attach to eclipses, sometimes correctly, and sometimes not: tides. Tides are real. They are measurable. They're an everyday effect of gravity and motion. And they do connect to the same alignment concept that produces eclipses, though in a calmer, more regular way. The moon raises tides on Earth because its gravity pulls more strongly on the side of Earth closer to it than on the far side. Earth's oceans respond to that differential pull, forming tidal bulges. The sun also raises tides, though its effect is smaller than the moon's because it's so far away. When the sun and moon line up during new moon and full moon, their gravitational pulls reinforce one another, producing larger tidal ranges called spring tides. Spring here doesn't mean the season. It means a springing up, an increase. When the sun and moon are at right angles during first and third quarter, their pulls partially cancel, producing smaller tidal ranges called neap tides. So eclipses and tides share a geometric theme. Eclipses require alignment near the nodes plus the right phase. Spring tides require alignment in general, at new or full moon, regardless of node position. That means solar eclipses always occur at new moon, and therefore they occur during the springtide part of the month. Lunar eclipses always occur at full moon, and therefore they also occur during spring tides. But here's the important calm correction. An eclipse does not create a special tidal force beyond what the new or full moon already provides. The tidal forces are about mass and distance and relative positions. The fact that the moon's shadow happens to fall on a particular strip of Earth during a solar eclipse is a light phenomenon, not a gravity phenomenon. Sometimes a solar eclipse occurs when the moon is relatively close to Earth, near perigee, which can make tides somewhat larger than average because the moon's gravitational effect is stronger when it's closer. When that happens, you can get an unusually high spring tide, sometimes called a proxygen spring tide, when perigee and syzygy coincide closely. But that's about perigee and alignment, not about the eclipse itself. The eclipse is simply happening under the same alignment conditions. This is a good example of how a hard science case file stays tidy. We let related phenomena sit in the same folder, but we don't let them borrow each other's causes. Eclipse, shadow geometry, light blocked or redirected. Tide, gravitational gradients, water responding. They can coincide. They can share timing windows. But they are different mechanisms. Now, one more layer of the eclipse story belongs to the people who use eclipses as tools, not just spectacles. Eclipses can be used to test models and measure subtle things because they provide sharp transitions, moments when brightness changes quickly, edges that move at known speeds. shadows that sweep across the atmosphere in predictable ways. During a solar eclipse, instruments can measure how the atmosphere responds to rapid changes in sunlight. Temperature profiles, wind shifts, changes in ionospheric conditions. The eclipse shadow is a moving perturbation, and the atmosphere is a responsive medium. Satellites in Earth orbit can observe the Moon's shadow crossing Earth's surface, an unmistakable dark patch moving across cloud tops and land. Weather satellites can track how clouds respond, how surface heating changes, how the boundary layer behaves. The eclipse becomes a temporary dimming experiment conducted by the solar system itself. If you widen the view beyond the ground, the eclipse shadow becomes something instruments can feel, even when no one is looking at the sun. Sunlight does more than illuminate. It powers chemistry and electricity high above the weather, helping maintain the ionosphere, a region where solar radiation strips electrons from atoms and molecules and leaves a layer of charged particles. That layer matters for radio propagation and for signals passing through the upper atmosphere. When the Moon's shadow races across Earth during a solar eclipse, it briefly reduces the sunlight driving ionization over a moving patch of sky. The response can be measured: changes in electron density, shifts in how certain radio frequencies travel, small variations in timing and phase for systems that depend on ionospheric conditions. This is one of the reasons eclipses appeal to researchers who study Earth's near-space environment. The eclipse is a natural experiment with a clean on-off shape. The timing is predictable, the motion is predictable, and because the dimming is rapid, you can observe how quickly the system responds, how fast certain regions recombine, how waves propagate, how the atmosphere above the atmosphere behaves when its energy input is briefly reduced. Lower down, the eclipse can also act like a short, controlled change in surface heating. Sunlight normally warms the ground and drives convection in the boundary layer. Reduce that sunlight quickly, and in some conditions you can observe small shifts, a dip in temperature, changes in near-surface winds, changes in turbulence. Not every eclipse produces the same atmospheric response because weather matters. But the eclipse provides a repeatable forcing pattern that helps researchers test models of how the atmosphere couples to rapid changes in heating. And because the eclipse shadow has a sharp edge and a known speed, it can be tracked in many ways at once. Weather satellites can image the moving dim region across cloud tops and land. Ground sensors can record the light level change and the temperature response. Distributed networks can compare measurements across distance and time. In a sense, an eclipse is not only something you watch, it's something Earth responds to, briefly and measurably, because sunlight is an input to many systems at once. And that brings us neatly back to the sun itself, where totality can open a short window onto the corona and chromosphere when the photosphere is briefly removed. For solar physics, totality can provide observations of the corona and chromosphere with reduced glare, and it can help calibrate instruments or provide comparisons to coronagraph data. Historically, eclipses were pivotal in understanding that the corona is real and structured. They were also involved in famous experiments, like the early 20th century eclipse observations that tested predictions about light bending near the sun. Even when the details of those historical events are complicated, the theme is steady. Eclipses make the sun's immediate environment easier to study for a brief window. There's another reason eclipse geometry keeps returning in modern science, even far from the drama of a darkened afternoon. In astronomy, an eclipse is a special case of a broader family of events called occultations and transits, moments when one object passes in front of another along our line of sight and changes the light we receive. On Earth, we experience that as a shadow on the ground, a sun turned to a crescent, a moon turning copper. But from far away, watching a distant star, the same idea becomes a measurement technique. A planet crossing in front of its star is in effect a tiny eclipse. The star's light dips by a small amount because the planet blocks a fraction of the starlight. If the planet is large compared with the star, the dip is deeper. If the planet is small, the dip is shallow. If the orbit is regular, the dips repeat with a steady period. And from those few facts, depth, duration, repetition, astronomers can infer surprisingly concrete things: the planet's radius relative to its star, the size of its orbit, the tilt of the orbit relative to our line of sight, and the planet's year. It's a gentler kind of eclipse, one you don't feel in the air and don't see as a shape in the sky. It arrives instead as a curve on a graph, a light curve, brightness over time. But the logic is the same as the logic in this folder tonight. Light travels. An object blocks some of it. The edges of that blocking are timed. The timings become evidence. And once you have timing, you can do something very case-file in spirit. You can look for deviations. If transits happen a little early or a little late compared to the simplest prediction, that can hint at other planets tugging gravitationally, altering the orbit slightly. Those small shifts are called transit timing variations. They are the same kind of clue as any small mismatch in a well-behaved pattern. They suggest there is another actor in the system, shaping the motion even if you can't see it directly. There is also a counterpart event, sometimes called a secondary eclipse, the moment when the planet moves behind the star from our point of view. Then the combined light we receive, star plus planet, drops by a tiny amount because the planet's contribution is briefly removed. That contribution might be reflected starlight, or it might be the planet's own thermal emission, depending on wavelength. Either way, the eclipse gives you a subtraction. It lets you isolate a small signal by temporarily removing it, which is one of the oldest tricks in careful measurement. And there is a third layer that connects back to lunar eclipses in a way that feels almost poetic, even though it's pure physics. During a transit, a small fraction of starlight passes through the planet's atmosphere before reaching us. The atmosphere absorbs and scatters certain wavelengths, leaving faint fingerprints in the spectrum. This is transmission spectroscopy, reading an atmosphere by the way it filters light along a long path. It's a distant cousin of the ring of sunsets that lights the moon during a lunar eclipse. In both cases, you are learning about air by watching what air does to light. So even when you step far away from the sun and moon and the familiar shadows they cast, eclipse geometry remains one of the most reliable ways to learn. Alignment becomes information. Motion becomes a test pattern. A brief subtraction in light becomes a measurement you can trust. With that wider frame filed away, we can return to the eclipses we feel closest to, our own sun, our own moon, and the short windows when their alignment makes the ordinary sky reveal an extra layer. For lunar eclipses, the moon's changing brightness and colour can be used as a probe of Earth's atmosphere. How much light is refracted into the umbra? How much is absorbed or scattered by aerosols? How the colour shifts. With careful modelling, you can link observed eclipse characteristics to atmospheric conditions. So a lunar eclipse is not just a red moon, it's a measurement of how Earth filters sunlight along the limb, a global sunset turned into data. At this point, the folder on my desk feels pleasantly full, but we can still slow down and add another layer, the geometry of perspective, and why eclipses are so location dependent. For a solar eclipse, The moon is close enough that its position against the sun changes noticeably depending on where you stand on Earth. Two people separated by a few thousand kilometers will see the moon shifted slightly relative to the sun because they are viewing from different points on Earth's sphere. That's parallax, the apparent change in position of a nearby object against a distant background when viewed from different locations. This is why eclipse maps show a path. It's not just that the shadow is narrow, it's that Earth is big, and the shadow is projected onto a curved surface, and your location matters. In a sense, a solar eclipse is a demonstration of near versus far. The sun is so far away that its direction is nearly the same for all observers on Earth. The moon is close enough that between Earth and sun is not a single line. It's a family of lines, slightly different for each observer. The eclipse is the moment when those lines align in the right way. For a lunar eclipse, the moon is far enough that its view is more uniform across Earth. If the moon is in Earth's umbra, it's in it for everyone who can see the moon at that time. The main variable is simply whether the moon is above your horizon. So solar eclipses teach location, lunar eclipses teach timing, and both teach scale. Now, we've covered the main physics. We could close the folder here and let the room go quiet. But for a sleep script, it helps to add a gentle drift, an extended, unhurried walk through the same landscape from slightly different angles. Not repetition as filler, but repetition as settling, like reading the same page twice and noticing new calm details each time. So I'm going to move through the evidence again, slowly, in the style of case notes, softened, reorganized, and stitched into a long, steady narrative that you can simply float along. Let's start again with the lamp. When I look at the desk lamp, it's easy to forget that the sun is not a point of light. But that's the heart of eclipse geometry. The sun is a disk. It has width. It has an edge. And because it has width, shadows have layers. If the sun were a single point, then any object blocking it would cast a shadow with a sharp boundary, and nothing more. Umbra everywhere, a clean line between light and dark. But because the sun is extended, the shadow has a gradient region where only part of the sun is blocked. That gradient region is the penumbra. It's the place where daylight becomes thinner without disappearing. And the antumbra is the place where the complete block fails by a small margin. The object is centered, but not large enough, leaving a ring. These are not poetic terms. They are practical terms. They tell you what you will see. Umbra, total eclipse. Penumbra, partial eclipse. Antumbra, annular eclipse. And then the whole story of eclipse rarity is simply the story of how often the moon's path crosses the line between Earth and Sun at the right moment. New moon is necessary for a solar eclipse, but it is not sufficient. Full moon is necessary for a lunar eclipse, but it is not sufficient. The moon must also be near a node, where its orbit crosses the ecliptic plane. So if you want to picture eclipses without diagrams, picture this: a tilted lunar orbit with two crossing points, two gates, and twice a year, a season when those gates are in the right place for alignment. We've already filed the details. Here, we just let the idea rest. When the timing is right, shadows become possible. That's the timing. Now let's let the solar eclipse play again. But this time, we'll focus on what the sun becomes during partial phases. Not a circle, but a crescent source. A crescent source casts crescent-shaped images through small openings. That's why leaf gaps paint crescents on the pavement. It's why pinhole projectors work so well. The eclipse turns the world into a camera obscura without anyone asking it to. The light also becomes directionally strange. Shadows can sharpen because the sun's effective shape is smaller. The ambience changes because the sky's brightness distribution changes. It's a subtle transformation, but people often notice it even when they aren't looking at the sun. And then totality arrives, and the experience shifts from dim day to brief night. The corona appears, faint but structured. Prominences can be seen, arcs of glowing plasma held by magnetic fields near the sun's limb. The chromosphere, the thin layer above the photosphere, can reveal itself as a pinkish rim for a moment around the edge. The reason you can see these things is not that they suddenly turn on, it's that the photosphere turns off, from your point of view, because the moon covers it. The moon is like a perfectly sized shutter. It blocks the bright part and leaves the faint parts visible. That's why total solar eclipses remain scientifically valuable even in an age of satellites. They provide a natural occultation, an occulting disk that can reduce scattered light and allow certain observations of the sun's near environment. Now the lunar eclipse plays again, and the lesson is about Earth. Earth's umbra is wide enough to cover the moon. The moon moves into it slowly. The darkness creeps across the disk. But at totality, the moon doesn't usually disappear. It glows. That glow is sunlight that has been filtered through Earth's atmosphere, refracted into the shadow, and stripped of much of its blue. Earth is doing what it always does at sunrise and sunset, scattering blue light out of long atmospheric paths and letting red light travel farther. During a lunar eclipse, you are essentially seeing every sunrise and sunset around Earth at once, projected onto the moon. And because Earth's atmosphere changes, clouds, dust, volcanic aerosols, the brightness and colour of lunar eclipses change too. Some eclipses are bright and coppery, some are dark and subdued. That variability isn't superstition, it's atmospheric physics. In this way, lunar eclipses connect the sky to the air around us. They remind us that Earth is not just a platform where we stand, it's an optical element in the system. Now, let's return briefly to the cycles, because they're a soothing way to finish. The notion that eclipses, while rare in any one place, are part of repeating families. The Saros is the famous one, about 18 years plus change. After that interval, similar eclipses occur because the moon's phase, node position, and distance repeat closely. The +8 hours shifts the visibility region because Earth rotates. 3 Saros cycles bring you closer to the same longitude. These are approximations, but good ones. These cycles don't make eclipses simple. They make eclipses trackable, predictable, fileable. And that's where the case file ends up back on the desk, where the office lamp can keep warming it. Before we close, there is one practical note that belongs in any hard science eclipse file, even in a sleep story: safety. For solar eclipses, you must not look at the sun during partial phases without proper solar filters. The danger is not discomfort, it's retinal injury. Eclipse glasses and solar viewers must be designed for direct solar viewing. Cameras, binoculars, and telescopes require proper solar filters on the front end. The only time it can be safe to look at the sun directly is during the brief window of totality in a total solar eclipse, when the photosphere is fully covered, and even then, only if you are certain you are in totality. Annular eclipses are never safe for direct viewing because the ring of sun remains. Partial phases are never safe for direct viewing without filters. For lunar eclipses, there is no such hazard. The moon's light is reflected sunlight, and when it dims, it becomes gentler still. Lunar eclipses are safe to watch with the unaided eye. That's the practical line, placed neatly at the end of the folder. And now we can let the office return to its own quiet eclipse. The desk lamp makes its small circle of day on the papers. Beyond that circle, the room is dimmer, softer. The shelves retreat into shadow. The window holds the night sky like a dark mirror. In this room, it's easy to see why eclipses feel meaningful to people. Not because they are messages, not because they change fate, but because they reveal how delicate alignment can be, and how much of what we call ordinary depends on light arriving uninterrupted. Most days, sunlight floods the world, and we barely notice the conditions that make it possible, the distances, the angles, the constant motion. An eclipse is a reminder that the ordinary is not automatic. It is maintained. It is a balance. It is a set of constraints satisfied again and again. And when, for a few minutes, those constraints are satisfied in a different way, when the moon slips across the sun, or when the moon drifts into Earth's shadow, the system shows another face. A quieter face, perhaps. A face with the corona drawn in pale lines. A face with the moon lit like old copper. A face that says, calmly, the universe is consistent, and consistency can be beautiful. So if you're still awake, you can let the last image settle. 3 bodies in motion, not rushing, not hesitating. A bright disk, a smaller disk passing in front. A shadow with a soft edge. Umbra, penumbra, and tumbra. A season when the nodes line up. A day when the timing is right. And then the alignment passes, and the ordinary returns, and the case file closes itself as gently as it opened. Back in my office, I slide the folder labelled Eclipses back into its place. The lamp hums softly. The window stays dark, and the world outside keeps moving through its patient arcs, carrying the next eclipse forward quietly, on schedule.